All right, guys. So we spoke of probability in this the philosophical sense of it, and here is the axiomatic approach for the subject. So what we have here is we imagine that we perform an experiment, and more so than an experiment, you have to imagine the universe. So we have a collection of all possible universes, and then we'll call that collection S. Okay, so S is just all possible outcomes of the experiment, and more so, it's all possible universes for the particular problem. Right, so that actually can be pretty dangerous. So if you roll a die, then you might say that this collection are the outcomes 1, 2, 3, 4, 5, or 6, depending on which part of the die is pointing upwards. Although, you see, you might argue, well, that's not the universe. Maybe if I roll the die on a brown table, that's a different universe, okay? As opposed to if I roll it on a blue table. If I do it in dark, it's a different universe than if I do it in light. So it does become, as you saw, I think I showed you some problems where you dismissed information that you considered irrelevant, and it was not irrelevant for the problem at all. The universe has to include all relevant information for the probability. So the safest thing to do, of course, is if you have the total universe, and then you start thinking which information is not affecting the universe and which is affecting the universe. In other words, when we speak about conditional probability, it will be chapter 3, you will see a little bit more of it. Right? You will see why I can make assumptions that I hold steady. In other words, I can assume that if I roll the die, then it's happening on a brown table, like what I have over here, okay? Rather than a blue table, because I can consider the possibilities of all other tables and see that in whichever universe I perform this experiment, I'm performing it in one of those universes after all, the result is the same. So that will be something to consider afterwards, okay? So you have to be extremely paranoid about the subject. If you toss two coins, the probability also, if you toss two coins, the spaces, the universes that will arrive are head-head universe, head-tail universe, tail-head universe, or tail-tail universe. You understand what I mean, guys? Those are the possible outcomes that will be created out of me rolling a pair of coins, or a coin twice. You might think it's the same type of universe. Coin twice or a pair of coins. So you make all sorts of simplifying assumptions. If you want to turn on a flashlight and see how long it works, the flashlight might be broken right away, in which case time it works is 0, or it can work a very long time, right? So the universe here are time interval between 0 to infinity. Okay? So this is a super universe. It's pretty cool. This thing is a super universe, and every element in that super universe of all possible possibilities, each outcome is a universe that comes to be realized, that comes into existence. Now, any subset of S is going to be called an event. An event might be one universe or a collection of universes that might take place. So for example, if S is a sample space of the lifetime of the flashlight, and we want to know what is, we want to consider only universes where flashlight worked longer than 5 hours. And then E is the subset 5 to infinity, okay? That means all the collection of all times. Each time is one instance of a universe, all times between 5 and infinity. Now, we know that the union and intersection of events is another event. Take any collection, intersect it with another collection, you get a collection which might be a universe or a collection of universes. So let's say that we consider the universe of rolling a die, and we want to consider the event that the number rolled is even. The number rolled is even will contain 3 universes. It's 2, universe where the die came up 2, or 4 or 6. So it contains 3 universes, 3 elements of the sample space. And if F is the event that the number is divisible by 3, then it's either 3 or 6. So then we can consider the intersection of those two events, and the intersection is the universes that they have in common, and that will just be 1, 6, just one universe in common. If we take unions, that will be everything in E together with everything in F. So this is also an event. And the empty space is an event. Okay, we consider that as basically we look at the power set, if you remember power sets of S. We consider all subsets that can exist there, and we will call in our class those subsets to be events. This is not entirely correct, but I'll mention about it below. Okay, so the complement of an event means that the actual outcome was not one of the outcomes contained in E. And that's defined to be the sample space minus whatever is in E. So for example, well, actually, the examples here are not that necessary, but let's just be sure, right? So for example, what is E complement? E complement means that neither 2 nor 4 nor 6 have occurred. So E complement will be 1, 3, and 5, I think. Okay? So that's what this complement thing is about. And then we have the following properties, which if you just realize what they mean, they are obvious. So if we have a union of a bunch of events and we take the complement, it means that the actual outcome was not one of this collection. And then it must not be in E1, not in E2, not in E3, all the way not to En. So that's the equivalent part here. We will use that later on. I hope you understand. If not, ask me questions.
Could you explain that again?
Yes, of course. Thank you for asking. So I use this abstract notation, right? But all it means is let's say, for example, suppose that I consider something that is in the complement of E union F. E union F. You see, the complement means that neither an outcome in E nor an outcome in F has actually come to exist, has been realized. Good. So what is that complement? That complement is the intersection of what's not in E and not in F. Make sense? So in other words, because by intersection, because not in E and not in F, and is intersection operation in logic. Make sense?
So would that be like 1, 2, 3, 4, 5?
So that will be the union. E union F will be 2, 3.
Okay,
4,
2, 3, 4,
6. Right?
6.
And then the complement will be 1 and 5.
1 and 5. Okay, got it.
Right. Makes sense, but that's just the union. Just the logical operations. They can be very many, and you don't want to go through them. You see why this is the equivalent statement. Basically, union means that let's say that I lost my cell phone. Okay, my cell phone is not in my house and not in the house of my friend. Okay, so what does it mean, right? So it's not there. It means union is it's a union. This event means the cell phone is either in my house or in the house of my friends. The complement of that means not in my house and not in the house of my friend. So the complement is the not, and intersection is the end. Do you understand why intersection is end, guys? All of you get it? Intersection is end because let's say I have brown eyes and you have brown eyes, right? So basically the bag containing brown eyes, if you imagine it this way, I'm carrying a bag having brown eyes and maybe other types of eyes, right? If I'm, not very sane. So I have this collection of eyes and you have some collection of eyes, and together in my bag there are brown eyes and in your bag there are brown eyes. That's how you think of it. By the way, inspired by a weird question. One person messages me. So there's a person that learns English, who knows in what place, in Indonesia, I think, right? For some reason, she picked me up on that thing, and I just helped her with some sentences. And her English instructor asked her to write reports about the Zodiac killer. I thought, there are people weirder than me. Right? I couldn't understand why Zodiac and why does she care about, no, she definitely doesn't care. She's whatever. She's obsessed about Christianity.
Wait, Professor, I had one question. I just don't understand like these letters, like K, N, E, K, C. Could you just clarify that?
Yeah, the letters, it's just index, right? Union, it's K1. Let's say it's a union. It just I list them by this K. It's E1, union E2, union E3, all the way to some end. So that's just abstractly talking about a union of several events, not necessarily two events, but maybe a bunch of them, right? And I just list them: the event 1, E1, the event E2, they're just collections. Okay, that's what it is. Good? Or no, I need to do more clarifications.
No, I got it now. Thank you.
I actually can try this thing. There were some glitches, but I have this stylus. I can try drawing things, right, and see if it works. Last time, though, I did it in my other class. It started flipping the screen, so I couldn't understand why. I haven't yet worked out all the glitches. Good? Are you with me, guys? Everybody understands everything I'm talking about, right? Sets and whatnot. Okay, so this is called the Morgan laws or something of the sort. So, and similarly, if something is in the complement of the intersection, it means it's either not in E1 or not in E2 or not in E3. It means that something is not common to every single event, right? There's something that is not in every single event. Good, and that means it's either not in E1 or not in E2 or not in E3, etc. Right? So let's say, imagine I have families numbered family 1 through family 10. And let's say that the first families, the family 1 through 9, they all have 2 children, but family 10 has only 1 child, okay? So I can say the property of having 2 children is not common to the intersection, right? Because if I look at all of them, I see something distinct. I see that somebody does not have 2 children. So that means either family 1 does not have 2 children, or family 2 does not have 2 children, or family 3 or 4. But we realize in my example, it's only family 10, okay? So, but in general, that's what this logical statement means. In other words, if you understand the statement, then it's not confusing, I hope. Am I right? Not confusing, guys. You have such poker faces. My God, you are waiting to play poker with me, I see, right? We are going to do that soon, I promise you. And we will see how good you are at my Kafka documents. Okay. So now we talk about axioms of probability. Okay, so probability is going to be, for our purposes, a function defined on the power set of S, where S is the sample space. S is just a collection of all possible outcomes. And the probability, in other words, what is a power set? Power set is just collections of all subsets. If you need afterwards explanations of what collection of all subsets means, it has to do with actually giving presents. In other words, that's how I would explain it. You see, you have S, it's like your collection of objects that you can give as a gift, and then you can choose which of those objects to wrap as a present. If you are very nice, you might give everything. So S is an element of the power set. If you are very miserly, you might have a package containing nothing at all. That would be the empty set. You can have one element in the set, or 2, or any combination of elements. Package them together, you create another bag, and that's your bag belonging to the power set. Everybody understands it, guys? I mean, I haven't talked long about power sets. I'm presuming you took some math classes or you know about such things. Am I right in my presumptions?
I personally never dealt with power sets, I think.
With power sets, but I will explain, okay? So it's not significant. In other words, what this means is that subset, any subset of S is an element of the power set, okay? So I will give you examples afterwards if you want. Anybody here want something? You know, stay for office hours, we discussed that. Good? Don't be quiet. Don't leave it to the last moment. Okay, so the axioms of probability are as follows. So first axiom is saying that for any element that you pick in S, in other words, for any subset of S, the probability is a number between 0 and 1. It's a function, you know, so it assigns every possible subset of S, it assigns it a number. Okay, between 0 and 1. Could be 0, could be 1. So far good? That means that there is some likelihood of this particular collection of outcomes to occur. It might be 0 likelihood, it might be 1 likelihood, it might be something in between. Then that's axiom 1. Axiom 2 is that this function will always assign the value 1 to the full set, because that means that why 1? Because you think one of those outcomes has to occur. correct? So if your sample space contains all possible universes, then one of those universes will be born, will come into existence. And the last axiom, Axiom 3, is the most complicated. And it says the following: if I have an infinite sequence of events and the events are disjoint, in other words, there is nothing in common between any pair of them, you understand? So it's a collection. If you have, let's say, a lot of markers, this is the bag containing one bag of markers, this contains other markers, and none of them are the same type of markers. Okay, good. So you understand what mutually disjoint means, correct? And then the probability of the infinite union, of the countable infinite union, is the same as the infinite sum. That's why I mentioned we need infinite sums of the probability. In other words, to come up with a probability of some outcome being in one of them, I just add the probabilities, which is very natural, you would imagine, correct? You would imagine that it's the probability that universe one occurs plus the probability that universe 2 occurs plus the probability universe 3 occurs if the collection is universe 1, universe 2, universe 3, etc. Right? So you imagine adding those probabilities. And any function satisfying axioms 1 through 3 is called a probability function. Good? And axiom 3, of course, is the chief reason why infinite series play such a big role in probability. Because you will often, when you use axiom 3, that's just an infinite sum that we considered when we did review of series. I hope the review was sufficient to teach you that concept. But we'll see. Okay, so there are many times where you can avoid doing infinite series. We'll show you how to do that. Okay, now one thing about the axiomatic approach, I mentioned that there are events that, there are subsets that have no probability. So it is true, you can prove it using real analysis, that if S is uncountably infinite, then there is no way to define such a function on the entire set. You understand? There are going to be subsets that will not have measure, that will not have probability, will not satisfy the 3 axioms. And that's what measure theory is about, and you consider truly the probability function to act on the collection of measurable sets. In practice, it's very difficult to imagine situations where that becomes relevant. You know, in some very theoretical, very complicated, deep study of probability, perhaps, but not in any examples that we are going to see. So we are lying a little bit and claiming that such a function will be possible. It's not. On the power set, there are going to be some subsets, perhaps, if the set S is big enough, there are going to be subsets that don't have probability. So that would be the measure. I don't understand the interpretation. I tried to give you, so many of you left, but I tried to give you the interpretation. Did you understand, guys, what I meant by my example with the probability not existing? I wonder. Did you think of it? I spent so much time drawing it. Okay. Fish eyes. Exactly, kind of. Yeah, so it's really good that I at least understand the myth of Tantalus and also of Sisyphus, right? The one who carries this boulder up the mountain. So that's my punishment. I just do things which I a priori know have no meaning whatsoever. Like I write those things to you, you don't read them, I spend this time, you know, absurd existence. All right, so here is the first example, guys. Let's see if you understand the axiomatic method and see if you could prove that, if you could figure out what's the probability of the empty set. What's the probability that when I run my experiment, nothing happens, no universe comes to existence. You understand axiomatically, right? So assuming axioms 1 through 3. You see this? Those are the assumptions you make about this function. In other words, you lose any sight, you're blind. You have no idea what probability means, any intuition behind it. You just have a function defined on some set S containing all possible outcomes that satisfies those properties. This is axiom 3. How do you prove that, what is the probability of nothing happening? The empty set.
Are we assuming the whole set is just the empty set?
Well, we're asking what's the probability of the empty set. So Sarkazi says the probability is 0. Wonderful, but the question is, how do you know? You are now lost all sense of intuition for probability, right? Like we did before. You are using axioms. I'm checking if you can think like a robot. Yeah, so by axiom 1, probability of the empty set has to be between 0 and 1. That we know, right? So axiom 1, empty set is a subset of S because it's an element of the power set. So we are saying it has probability between 0 and 1. There is a number assigned to it. But how do I know what number is assigned to the empty set? Some of you guess it, of course, right? When I run the experiment, we are assuming a universe will come into existence, one of them. So the probability of nothing coming into existence should not be, right? It should be 0. But why? Why would that be true axiomatically? Well, how can I assume that, Naomi, right? I cannot make extra assumptions. I have to stick with what I have. You have to use all the axioms, perhaps. Well, you can decide which you prefer to use. The book had one way to solve it. I think I wrote it, but I have another way. Yeah. So your argument, Shabeli, I really like it. The only problem with it is that Axiom 3 requires me to use infinite sums. I cannot use finite sums. If I could use finite sums, your argument is perfect. The problem is, what if I have to use infinitely many sums? Can you do that? Stephen R, are you here? Stephen R. Stephen R is an interesting person here. Okay. There are some people that like to log in without being part of the class. Interesting. Good that I check. So the union of all events is equal to the sum of the probabilities of all events. That's Kazi says that. Well, your statement is a little confusing, right? Because union of events in probability is something else. You might have very good thoughts about it, but not quite expressed it the way I'm looking for it. So let's do it together. Or do you want to think a little longer? Okay. This beast is trying to get into my room. Do you hear it? It is there. So here is my suggestion. Okay, so there is one that was done by your book, I think. I would do it this way, guys. So empty set can be written as a union of empty set, empty set, empty set. Agreed? So I can say that E1, E2, E3, all of them are empty sets. E1, E2, E3 are empty sets, correct? You are with me, guys? So I just said the same set. I say E1 is empty set, E2 is empty set, E3 is empty set, E4 is empty set, forever. Okay. By axiom 1, the probability of the empty set will be a number. It will exist. Correct. We know that this probability of empty set exists because we have this statement here, axiom 1. Where is it? Axiom 1. This one. Yeah.
Yeah.
Good. So what can I do? I can simply write the unions of empty set, and then they are mutually disjoint. Intersection of empty set with any other empty set is empty set. So this probability is equal to the series k1 to infinity of the probability of the empty set. In other words, I'm adding a constant convergent sequence. And if I'm adding a constant convergent sequence by the divergence theorem, that means that the terms of the sequence must go to 0. Do you remember? So if when I add, I have empty set, probability of empty set, probability of empty set plus empty set, probability of empty set plus empty set plus empty set, and that must tend to a fixed number. But I'm adding the same thing, the same number. So how could that possibly happen? The distance between the rows has to go to 0. If I'm adding a constant term, that means the distance between one row and another is already 0. You follow? Otherwise, I would always be able to tell apart one row of a sequence from another row of the sequence because they will be at an equal distance apart. So that at equal distance has to be distance 0. Otherwise, it's not going to work. So that means that this limit is, well, that means that what I'm adding is just zeros. Did you follow my argument, guys? No? Okay. Let me just go back from those notes and go back to review of infinite series. Do you remember what is a sequence? Here is a sequence. Okay. A sequence can be thought of as a table with infinitely many rows. It's one column with infinitely many rows. Here is row 1, 2, 3, etc. When I say that a sequence converges, it means that starting from one row onwards, the rows look exactly alike. Are you with me? So rows, I picked a very simple sequence. I picked 10 to the power of minus n, because then you can write away, let's say if I can see those first digits, everything that's afterwards will look to me like 0. So 6, 7, 8, they're not true zeros. There is a 1 here, but they look to me like a true 0. Good? Now, what is a series? The way we understand series in calculus is that it's a kind of sequence. Here is how we understand series. So instead of don't think of the sum, we have a first element, sum of first 2 elements, sum of first 3 elements, sum of first n elements. You see? So that's a new type of sequence. It's a sequence of partial sums. Do you agree? Now imagine that sequence of so I draw the same column for the sequence of partial sums. That column. Right? Either the rows of that column start looking alike, or they are not ever looking alike. Okay, in other words, to any particular observer, to any detector, no matter how precise is the ability of the detector to tell one row apart from another, that's your epsilon value, right? No matter how precise that ability is, eventually the detector will conclude that all the rows start to be the same. So for this procedure, a detector that can detect the first several digits starts thinking that rows 6, 7, 8, 9 are the same number 0. Of course, they are not. Okay. So if I were having the series, that means that that the nth partial sum, the n+1 partial sum, the n+2 partial sums, they all look the same. Do you agree? They all look the same. Now, how could it happen? What's the difference between the two partial sums? It's the a-nth term. It's the next term that I add, right? So between first and second row, it will be the distance between them will be a2. A2 is how much they are different. Between 2 and 3, the distance is a3. Between 3 and 4, the distance is a4. A is the term of the sequence that I'm adding. Now, if they become alike, that means that the difference a1, a2, a3, a4, it has to be going to 0 because the rows have to be the same. Otherwise, this distance will be kept apart. We'll be keeping those two rows from looking alike. You understand? That's the divergence theorem. Did I make sense, Valeria? Your eyes tell me somewhat not entirely. You see, I haven't lost my ability to read people's faces completely. Okay, but so we will continue talking again. If you stay with me after class.
Wait, why is it? What are we supposed to know that?
Of course. I
mean from previous classes.
Yes.
Really?
Previous, of course. That's calculus.
But then probably like this 212 probability I took. I don't remember this, but I remember the Morgan's law.
Yeah, but probability. So here is what, not from a probability class. Probability class is, I'm not sure what was the previous class. There is no previous class to mine. So there is Calc 2. In Calc 2, you learn infinite series. When you learn infinite series, you understand the divergence theorem. It's this theorem, guys. Where is it? Divergence theorem. I wrote a review of it. We can talk about it after class. It's very easy to get what it means. You don't even need to know it. At least I believe I'm good enough to explain it to you pretty fast. Okay, so the divergence theorem is this, right? If the series converges, the partial sums converge, that means that the terms of the sequence that made it up, this A2, A1, A3, that means that the sequence goes to 0. If it doesn't go to 0, the series cannot converge. That's the idea. That's called the divergence theorem. And here is a proof of it. You see, the proof of it is Sn equals to the partial sum. An is the difference between Sn and Sn minus 1. If I take limit of n, this limit exists and is equal to S, and this limit exists and is equal to S, so it's S minus S is 0. It means that the terms of the sequence must tend to 0. The an must tend to 0. Yes? What you're adding must tend to 0. And I can see that very easily because what is the an's? Those are the distances between one row to the next row. It's this, right? So this is, so here I used A1, but imagine it's S here, right? So the distance here is A1, the distance here is, distance here, sorry, is A2, this one distance is A3, A4, A5, etc. So the distance between them must be going to 0 if the rows are to look alike for the summation. So that's your divergence theorem in a nutshell. So just to quote, guys, type in the comments if you understood what I just said.
I have a question.
Yes.
So in the notes, you said that by axiom 1, the series converges. Why? Yes. Why is it by axiom 1? How does axiom 1
because
show?
any subset, probability will make any subset, well, the probability function will assign a value between 0 and 1 to any subset. This is false, by the way. You are right to not believe this argument, right? Because why don't you want to believe this argument? Because maybe that's why the book did it slightly more convoluted way than what I'm presenting, right? The reason is that it's not possible in general to assign probabilities to every single subset. You can prove that you can assign it to the empty set, but that's another story. See, but if we pretend that that doesn't exist, if you pretend that you can assign probability to every subset, then there's no problem. So it's possible if it's a finite set, if it's a countably infinite set, I think, right? But if it's very large, if it's like large enough like the real numbers, then you cannot do that. Okay, so that's why the book, I presented two proofs there, but the one I'm presenting here, I think it's quicker, giving that assumptions 1 through 3 will hold. Good. So guys, only one person said understood. That means that the others did not. You should have taken calculus with me. Okay, still, what is it, 3? Or you're just your finger is working. You don't want to press yes. All right. And stay after class, guys. We can talk about so many wonderful things.
Calculus 2 is the most brutal class.
Mine?
Calculus 2. No, overall, out of all the classes.
No, I mean, you haven't seen Pluto. No, calculus 2, you see that the thing is, those things are much easier than what they appear. If you realize what they are, so let's say, when I say power series, right? What is that big word? Power series, you might think, oh, what is it? But what is power series? It's a polynomial. It's an infinite polynomial. If you understand what polynomials are for and what you're trying to accomplish, then the entire idea is clear. Okay? It's just when you understand something, it becomes obvious to you what is it people are talking about, and then you think those big words are kind of not necessary. Anyhow, so good that you understand why the series converges by axiomatic converges, assuming we can assign probabilities to every subset. And then since it's a constant convergent sequence, I'm adding a constant sequence, that means that each row is at the same distance from the next row, right? So the rows representing partial sums are the same distance apart from one another. And that distance has to be 0 in order for the rows to start looking alike. So that means that what I'm adding is 0. Good? Shotaro, you understand me or no?
So each of the EKs are going to be the empty set then. Is that a given, or like what?
I can decide, because I need to add up probabilities of events, and the events have to be disjoint. Disjoint means their intersection is the empty set. So
okay.
I'm going to select them to be the same thing, the empty set.
And also the EK doesn't have to be unique then.
Well, except for the empty set, it does, because if it's not unique, then E of 1K and then EJ intersection will not be empty. So except for the empty set, they have to be unique.
Okay.
Because if I have the same set that's not empty repeated, then I will have a non-empty intersection between at least two of them, right?
Okay, I get it now.
The only way for them not to be unique is if all of them are the empty set. Or of course, I mean, you can have some of them unique and then afterwards followed by a bunch of empty sets. That's fine.
Okay, yeah, because it just has to be the subset. Yeah, I get it now.
Okay, so I'm not going to torture you about axiomatic things here, but you understand why probability of the empty set is 0, given that the ideas that we described, correct? Okay, so now your next challenge is this, guys. Suppose now, and that's what Chabeli's argument was actually pretty wonderful, it's just used finite sum. So now in axioms, we're forced to use infinite sums. So what about if we have finitely many events and they are mutually disjoint? What do you think is the probability of the union of those events in terms of the probabilities of individual events? What do you mean one, Shotaro? So they are not necessarily adding up to S. They are just some subsets that are disjoint from one another, but finitely many of them. And you want to know what's the probability of the union in terms of the individual probabilities. Yes, know me, but why? Wonderful, Kazi. The question is, of course, why, right? We are now robots, we have no intuition, and we are trying to see why that's true based on the axioms. Axiom 3, but how do you apply it? You are possibly right, but Axiom 3 only works with infinitely many sets. For Axiom 3, you have to have a sequence, a countably infinite sequence with infinitely many sets, and somehow now you have to speak about finitely many sets using it. Steven, are you here? Steven R. Dieser Mann ist ein Simulant. That's from Schweg, if you know it, right? So this person is simulating.
Maybe he's in the bathroom.
Yes, he better be there for the rest of the class.
What's
Professor?
pairwise disjoint?
Sorry?
What is pairwise disjoint?
Pairwise disjoint meaning there is nothing in common, right? So let's say, what languages do you speak? Let's say, what language do you speak? Kazi, I think, is speaking to me, correct?
Yeah, I speak English, Bengali, and a little bit of Spanish.
Okay, you see? So we are not pairwise disjoint in terms of the languages we speak because we both speak English, right? But if you pick another person that doesn't speak any of my languages, speaks other languages, then we have a pairwise disjoint collection of languages together. Yes? So pairwise disjoint, let's say, imagine that we have that's actually how I often feel. Imagine that every single person in this class spoke an entirely different collection of languages, right? And then I'm talking to you and you're talking to me. We don't ever understand each other. That's pairwise disjoint. So they take every single person as a separate collection of languages. So any you just pair me and you, or Naomi and Valeria, you pair any people together and they don't speak any languages in common. That's pairwise disjoint.
Right. That's a really good explanation. Thank you. Yeah.
Sure.
Professor?
Yes.
So could we think of this problem, like, so this is just a part of the, like, if we have some kind of infinite infinite sum, this is just one part of the, the sequence of partial sums.
So say it again, I'm sorry. Repeat your statement.
So, because Axiom 3 has to deal with infinite sums, if we make this into from 1 to n, that's just a part of the infinite, if that's just part of the sequence.
Yes.
And then we just kind of assume that, like, e to n plus 1 all the way to infinity is also disjoint as well. That would have to also equal. And then,
so what do you do with the next, with the others? You have to have a summation that contains infinite many of them. I'm sorry, when I get distracted, I'm hearing this beast screaming outside of my door. I'm not sure if you're hearing it. Yes.
So I guess going off what he was saying, would the everything after e plus 1 just be like a sum of empty sets?
Yes.
And so it
Brilliant.
would just be
Brilliant.
0?
Brilliant. And also
Okay.
the 0. Thank you so much. Brilliant. Apologies if I am floating. But yeah, so all you do is just set all the remaining ones to be empty sets, and then you now have a finite sum, because just add the remaining ones are just a bunch of zeros, correct? Good? So we understand how to do this problem, correct, guys? It's very simple now. Now that we know that the empty set has probability 0, we can make any finite collection of pairwise disjoint sets into an infinite one. And then we can just use Axiom 3. So Kazi was correct, Axiom 3, with just this extra property that empty set it has probability 0. It means that something always happens when you do the experiment. And so now, guys, let's talk about this proposition, right? So some simple propositions. What's the we want to prove that probability of the complement is 1 minus the probability of E. So probability E complement, it's 1 minus probability of E. Can you figure out how to do that?
if we make E plus E complement equal the set, the entire set, and then just kind of separate out the sums, basic algebra.
Brilliant, basic algebra. S is always equal to the event. No matter what, an event happens either in E or not an event. An outcome happens in the event E or in not E, correct? So they are pairwise disjointed. We already know that we can add any finitely many. And now we can do what Shabeli suggested and what Kazi suggested. we can now say the probability of S is 1, and that's the probability of this pair union of those pairs, and they are disjoint, so that's probability of first plus probability of second. And so now basic algebra, I move it around. I have that probability of the complement is 1 minus probability of E. Makes sense, yes, guys? You see, we're building this axiomatic thing. It's wonderful. We're pushing forward. The problem is, what are we really establishing? What are those numbers supposed to signify? That's the problem. Okay, so now another proposition. Can you see it, guys? Let's prove that probability is increasing. If E is a sub-event of F, prove that probability of E is less than or equal to probability F.
Would this be the same thing?
What do you mean the same thing? Maybe
Like,
same
you
thing.
would say that E, and then there's the complement of E, and then you would set the probabilities of E and the complement of E to be equal to 1, but then the probability of F, since F is the entire set, is 1.
F is not the entire set. F is just bigger than
Oh,
E.
okay.
You see, so we want to show the probability is an increasing function. In other words,
Okay.
the probability of a sub-event of another event is less than or equal to the probability of that event. Paula, you look sad. By what, Paula? What are you confused by? Of the axioms? No worries, no worries. So how to pick very good set of axioms, that's complicated, of course, right? But think about probability is very much the same concept as area, okay? But we have a restricted area. So in other words, the biggest space we have is S, and we normalize its area to equal to 1. That's axiom 2, okay? So in other words, imagine we're trying to measure areas that are sub-areas of some fixed region, okay? And so then you would imagine that any sub-area of S will be between 0 and 1, okay? Because E is a sub-area. In other words, imagine you're having your house, you can be anywhere in your room. So that's the area of your room is normalized to be 1. Then if you take any particular region where you're walking, that's a region that is traced into E. And that region has area between 0 and 1. It has to have area not bigger than 1, and it cannot have negative area. Make sense? So this is really talking about area. And then if you have several disjoint areas, you would imagine that the combined total area is the sum of each of them separately. Okay? So probability, that's the insight. It functions exactly like area. Like all the ideas you have about area, which is the properties of measure theory. So did I clarify a little bit? If it were about area, you would understand those axioms correctly, correct? Yes, axiom 3. Well, you know, so in mathematics, they really like to add to infinity. They just cannot do without it. So you see, an infinite sum can capture finite sum. In other words, if you could add things to infinity, or if you could have infinitely many summands, you can simulate finitely many summons, as we just proved below. Okay, so but if you have just finitely many summons, you cannot necessarily simulate an infinity of summons. So so this is basically just the idea of Axiom 3 is that if you want to measure disjoint areas, right? If the areas do not overlap, you just add one area plus the other area plus the other area. And the reason it's infinite is just so that you could actually carry out more interesting calculations. I can give you more examples from analysis about it. Great. Yes, Abhishek, very good. Very good. So let's do it together, guys. Where is it? So here, right? So all you have to do is just again, right? What is F? F is it's just the intersection of S and F, which is the intersection of E union E complement with F. And that's the same as E intersection F union E complement intersection F. But E is a subset of F. So this intersection is simply E. You see, this intersection is simply E. Probability of F is then E plus whatever is not in E but still in F. So it's pretty kind of clear even without doing this logical thing, right? So if F is bigger, it's whatever is the area E plus the area that does not include E but still is in F. So we have this, and we know we have finite addition, you see? So really you think area, if there are finitely many disjoint sets, their addition will be, you know, you would just have to add one area plus another, but the reason you do it to infinity is because you can then have more flexibility. So now this is now easy, look at it. From here, this guy is just another event, and events are always non-negative. So you see, I might be increasing this probability or I might not changing it. Maybe it's zero. Maybe it's zero probability. But regardless, I'm not going below probability E. So you can see that probability F is bigger than or equal to probability E. Makes sense, yes? And thank you, Abhishek, for your suggestion. Here is the next proposition. We're almost done with this chapter. I find this axiomatic thing slightly boring, but what follows is more exciting. But we're almost done. We do have to cover this idea, guys, right? So then suppose that I want to calculate probability of a union of two events. They don't have to be disjoint. There might be overlap. You agree? So the region contained in two areas, those areas might, like I'm showing in this video, overlap. Obviously, if they don't overlap, it's first plus second. Class over at 650, correct?
Yeah.
Yes, we'll do it together. So logic. Yes, logically it makes sense. I actually dreamt I had a stroke. Yeah. So this is one way to do it is you can draw a Venn diagram. You know how to draw a Venn diagram. I'll just quickly do one for you maybe. So Venn diagram, you just have event E and overlap event F. And when I add the area, I add the overlap twice. Agree? So this is probability of E means add the area E plus probability F. I add the area F. I added this region twice. So that's, I need to subtract it. This is the intersection. So I subtract it. So that's using Venn diagram. That's pretty obvious. Good? But I don't like Venn diagrams. So here is the argument without a Venn diagram. So E union F can be written as E together what's not in E and F, right? You understand what those are disjoint sets, agreed? So I just take E and then add whatever is left that was not in E but is part of F, so that I don't need to add twice. So then the probability of those events is addition, it's fine. Yes, and so I now need to calculate probability of E complement F. The probability of E complement F, we already did this calculation. So F is it's the same as EF and E complement F. So probability of F is probability E and F plus probability E complement F. So then to solve for this guy, I just move the second guy across the equal sign. So this probability E complement F is probability F minus probability EF. You see, I just replace this guy with this expression. Make sense? So proof is complete. But I just made two calculations. I made it disjoint, and then I try to rework what is this thing. So far with me, guys? Make sense what's happening? Great. So now let's see what happens if I have 3 events. Venn diagrams for 3 events already become ugly. We don't need to do that. We can just use recursion. Look at it. If I have unions of 3 events, I can consider this as a union of 2 events. I put in red brackets 1 event, and separate is the remaining event. So probability of union of those 2 events is probability of E union F plus probability of G minus probability E union F intersect G. Make sense? I'm just using this, I derive this formula, I now can use recursion. I can reduce 3 unions to 2 unions and just apply the same idea several times. So now, what I underlined in blue, I already know how to calculate. What is in blue is just union of 2 events, so we just work it out. Good. Plus probability of G. And so now I need to take care of this remaining guy. What's probability E union F intersect G? So that's the same as E intersect G and F intersect G. Good. And what's that? Now I just reorder it. So it's probability E plus probability F plus probability G. Now minus probability EG, it's 2 events, EG minus probability FG. And because I'm just using, you see, when I just look at this thing without parentheses, it's probability of first plus probability of second minus the probability of the intersection of those 2 events. So this is first event, second event, and minus minus is a plus, the intersection of all of them. So EG, FG, G and G, it's just G, E, FG is what we have here. Make sense? So this is the formula I obtained for union of 3 events. So I just add up the singletons, then subtract every possible pair, and then add every possible triple. You should see that this is indeed the general pattern. We will need to develop a general formula for a union of n events. I'll show you examples where that comes in handy. Good. So that is the formula that we have if we have n events. It means, you see, it means that what you do is you first add up all the singletons, then you subtract every pair, and then you add every triple, and then you subtract every combination of 4, and onwards. You understand? Until you get to n. That's what this summation is supposed to mean. So the summation is taken over all possible n choose r elements. Let me just give you an example before I explain further. Look what happens here, guys, right? So suppose I have 4 events, E1, E2, E3, E4. So how do I calculate the probability of the union? That's the summation of the probabilities of the individual events. You see, we have only 4 of them, minus any combination, any pair. So there are going to be 6 combinations. I have E1 combined with E2, E1 combined with E3, E1 combined with E4, then E2 combined with E3, E2 combined with E4, and finally E3 combined with E4. So any pair of events has to be subtracted from here. And then plus all possible triples. So there are going to be 4 of them, depending on which element is missing. And then finally minus all possible 4s. So that's how this formula is supposed to work. You understand what this formula means now? So it will come, we will use it in a few lectures. We are going to use this formula. So make sure that you understand why that works. Convince yourself it's true. You see, it's definitely true for 3. You can use induction if you prefer, or just again, you realize the pattern here. The pattern is add, this is what this means. Add every singleton, subtract every pair, add every triple, subtract every combination of 4, and so on and so forth. So that's just a way to write it as a sum. Okay, and the denominator, what you have here underneath the sum, it just means that when you select the R combination of intersection of R terms, you can order them from the smallest index to the largest index, and that's what this is doing. That's why whenever you make a choice out of n sets, you make R sets that you choose to intersect. You can write the intersection starting with the smallest index and going to the largest index among what you have selected. So this scary looking formula makes sense to you guys? Yes, and you don't need to remember it, right? You would be able to quickly figure out what that formula is, right? Well, an easy hint is this: it's already clear what happens when you do it with 2 events, right? It's add every singleton, subtract every pair, and then it goes add every singleton, subtract every pair, add every triple. It's easy to remember. Correct? Wonderful. And here is, so here is a question. I have 2 cats. Cat A irritates me with probability 0.95. Cat B irritates me with probability 0.01. What is the probability that I will be irritated by neither cat? Assuming, of course, that the probability that both cats irritate me is 0.005. Go ahead, calculate. Wonderful. Oh, you see, you're so good at it. Do you hear him? All right, let's see what's the answer. Okay. So first of all, the probability of being irritated, it's either A or B happens, right? In other words, I'm irritated by either A or B. That's a union. This is the event I'm irritated by A. This is the event I'm irritated by B. The intersection means I'm irritated by both. So I'm getting irritation at me from both guys. So that's 0.95 plus 0.01 minus 0.00, and that's this number, correct? Yeah. And so what happens next? Next, the probability I'm not irritated by any of them is 1 minus the probability I'm irritated by any one of them. So that's 1 minus blah, which is this number. Good? Okay. So what about, let's start with having 3 sample spaces. All right, so next lecture, we will only do a little bit of it today. It's a long lecture, and we are dealing with sample spaces having equally likely outcomes. So those are the ones that it's easiest for us to figure out probabilities for, okay? So it's also often reasonable to assume that every outcome in a sample space is just equally likely to occur. And if that's the case, suppose the sample space contains just finitely many possible outcomes, outcome 1 through outcome n. And then what's the probability that outcome 1 will happen? It's going to be p of 1. Probability that 2 will happen is p of 2, and all of them are the same number. So probability function assigns to each node, each universe, the same likelihood. Good? So it's in this likelihood is some number p. What's that number p? Well, by the axioms that we just did here, we know that the probability of the sample space is 1, and this sample space is the union of the singletons, correct? Yes? And so I can use this finite additivity property, which I proved. So what I have is just summation of p plus p plus p for each of them. This is p plus p plus p. They're n copies. So 1 is equal to p times the number of universes, which means p is 1 divided by the number of universes. It's just like some people said in the previous class. It's 1 universe out of n possible universes is our probability. Right? So that's true when every option is equally likely as another. Make sure not to confuse that. If you have 2 possibilities, the probability of the possibility here is not necessarily 1/2. That's only true if they are equally likely. Good? And that makes calculation of any event, of the probability of any event, simple. It's just the number of outcomes divided by, in other words, numbers of universes that correspond to success divided by total number of outcomes. Good? Let's try to figure out this probability, guys. If 2 dice are rolled, what is the probability that the sum of upturned faces is equal to 7? And I want you to start from the very beginning. I want you to produce Kafka documents. You don't have to do it for all questions, but on the exam, I would appreciate you doing it like I will show in my exercise. So you understand what you are supposed to do here, guys. So the dice are fair. So how many universes are possible? The universe is the outcome on both dice. Yes, Abhishek, correct. So not only by the way we make it correct, but make it correct so that when you have difficult problems, you will not make mistakes. Okay. So here is my Kafka document. For this, it's a bit lazy to do it. It's a bit tiresome to do it. But my universe is, first of all, my universe is outcome of die 1 and outcome of die 2, right? So that's how I specify on my document. Once something happens, I record it on a document and I write die 1 here, I write the value that I obtained, and on die 2, I write the value obtained. So my universe consists of those two outcomes. And clearly by the basic principle of counting, it's 6 times 6. So I have 36 elements of the universe, correct? So number in S is just 6 squared. Now, how many correspond to outcome E? Very simply, okay, so I can just record the number in die as K, and then the other number has to be 7 minus K. And because 7 is bigger than 6, I can make K equal 1 all the way to 6. So by that, I know that there is, as soon as I specify the first outcome, the second is immediately given to me. So the answer is clearly 6 divided by 6 squared, which is 1 over 6. Correct? You understand what I'm saying? For this problem, obviously, it's kind of long, but I want you to develop a precise way to be sure that you haven't made a mistake. And the way I do it is using those documents. So first of all, let's understand what the word random means, guys. So the word random, I will tell it, I would assume it means indifferent. In other words, each outcome is just as likely to occur as any other outcome. So when I use the word random, I mean nature is indifferent to the particular outcome to happen or not to happen. So it's giving each of them the same opportunities to come into existence. So here is the next question. Let's maybe do this one last question. 3 balls are to be randomly drawn from a ball containing 6 white and 5 black balls. What is the probability that one ball is white and the other are black? So you see, Shabeli, you're beginning to ask interesting questions. You say, well, this question might be vague, right? Replacement, non-replacement. What is happening here exactly? So 3 balls are randomly selected. So let's say this. We'll interpret it to mean that basically we just run this experiment, and there is going to be an outcome at the end of it with each ball without replacement, listed, the 3 of them that I picked listed. We shall see, Valeria. So guys, your time is up for today. So Kazi, you are using multiplication, and that's conditional probability. We haven't talked about it there, right? When you're using this, that means you're not using the Kafka method. It's dangerous. Even if you are correct, you see, you need to develop procedures to make sure that it's always right. All right, guys. So I will say goodbye to you. We can talk in office hours. We will solve this problem the next class. It's already 6:53. I don't like keeping you more than I have to, unless you want to stay, then I do. Okay, so I'll stop the video. And if you want to continue talking about something or solving exercises, just stay.